1's and 2's complement are two different processes used to represent negative numbers. So let's take a look how 1's complement is used to represent negative numbers. So let's say we have a decimal number 4. So basically, decimal number 4, we can rewrite this in binary in 0, 1, 0, 0. But what is the negative equivalent of negative 4 in binary? So to do that, we have to use the 1's complement. So the first step that we need to do is to copy this binary form of 4. There you go. And then we'll invert each bit of this binary. So we have 0, so we have to turn 0 to 1. And then another 0, turn this again to 1. So we are inverting each bit we have on this binary. Then for 1, so the inverted value of this is 0, and 0 becomes 1. So therefore, in 1's complement, 0, 1, 0, 0, so these are the binary, 0, 1, 0, 0. If we will turn this into negative, it becomes 1, 0, 1, 1. So this is now the representation of negative 4 in decimal. So let's take another example. So let's say we have positive 7. In binary, we can write this positive 7 with 0, 1, 1, 1. Now let's have a look on its value if we will turn this into negative 7. So for now, we don't know the value of it yet. So for us to see the negative representation of negative 7 in binary, we will copy this number. So let's copy that. So we have now copied the binary numbers and then invert each bit here. So let's start with 1. So invert this becomes 0. Then this becomes 0. And then next, still 0. And then the last part, this becomes 1. So therefore, in 1's complement, negative 7 is written as 1, 0, 0, 0 in binary. So let's have another example. This time, let's try to solve 0. So basically, in binary, this is written as 0, 0, 0, 0. And then, if you will apply 1's complement for 0, then this means that all these 0 will become 1. And it will appear as if we have two different 0. A positive 0 that has a value of 0, 0, 0, 0 in binary, and a negative 0 that has a value of 1, 1, 1, 1, which in reality is not really part of mathematics. We don't have negative 0 in our math. So it means that 1's complement has some drawback in terms of handling negative numbers in binary. Let's have a look on this table. So we have here two columns, the signed number for decimal and another column for 1's complement. So positive 5 is written as 0101. Okay, so it was written as 0101 because we know that 0101, so this is 1, 2, 4, and 8. So we will have to cancel out those zeros. So what will remain is the 4 and 1. If we will add this, 4 plus 1, this will give us 5. This will give us positive 5. So that is why positive 5 can be written in 0101 for binary. Now, what is the negative 5 in binary? Now, let's try to use 1's complement. So we need to invert all the bits. So 1 becomes 0, 0 becomes 1, 1, 0, and then 0 becomes 1. For positive 3, so we can rewrite this in 0, 0, 1, 1. So if we will add this, we have 0, 0, 1, 1. And then let's write the equivalent of each bit here. So this is 1, this is 2, this is 4, and this is 8. So we have to cancel those zeros. So we don't need this one, we don't need this one. So what is left is the 2 and 1. So let's add 2 and 1, this becomes 3. So that is why positive 3 is 0, 0, 1, 1. Okay, so the negative 3, so all we have to do is just to invert each bit. So 1 becomes 0, 1 is 0, and all 0 here becomes 1. Okay, for 0, it can be written as 0, 0, 0, 0 in binary. But again, we have this negative version because if we invert 0, 0, applying 1's complement, it will give us 1, 1, 1, 1, which means that our 0 has two different versions, a positive 0 and negative 0, which in reality, we don't have these cases. So that is why I will introduce you to the 2's complement, which is more accurate than 1's complement. So let's say we have 4. So the binary form of 4 is 0, 1, 0, 0. And to get the negative 4 using 2's complement, what we will do is that we will apply 1's complement to this number here. So for now, we don't know what the value of our 4, the negative 4. So let's copy the binary form of 4. There you go. After copying, we have to invert each bit of this. So we are applying 1's complement. So invert. So we have 0 inverted becomes 1. 0 again becomes 1. And then 1 becomes 0. And then 0 becomes 1. After inverting, we have to add 1. For now, I haven't taught you yet how to add binaries. We have a separate topic for addition of binary numbers. But since addition of binary numbers is part of this complement, let's take some basic step on how to add binary numbers. So 1 plus 1, this is basically 2. So 1 plus 1, basically this results to 2. And 2 can be written in binary as 1, 0. So this is 2. How can we say that this is 2? Let's write here. This is 1 and this is 2. Then we have to cancel those numbers with zeros. So what will remain is just the 2. So it means that 2 can be written in binary as 0, 1. So this means that 1 plus 1 in binary is, this gives us 0, and then we have to carry the 1, and then 1 and 1, this becomes 0 again, then we have to carry 1, and then 1 plus 0, this becomes 1, and then just bring down 1. So this will give us a value of 1100. That is now the value of our negative 4. Alright, so let's have another example. So let's say positive 7. So positive 7 can be written in binary with 0, 1, 1, 1. If you want to check how these numbers becomes equal to positive 7, it's because we have 1 here, 2, 4, and 8. And then we have to cancel those numbers having a value of 0. So what will remain is just the 4, 2, and 1. So add this all, so it will give you 7. So that is why 7 can be written in binary as 0, 1, 1, 1. Now, what is the value of negative 7 in binary? So let's try applying 2's complement so that we'll be able to get the negative binary value of negative 7. So we don't know the value of negative 7 yet. So the next move that we will do is to copy this. There you go. And then after copying, we have to invert each bit. After inverting all the bits, then we add 1. So 0 plus 1, this will give us 1, and then just bring down all the remaining bits. So it means that negative 7 has a value of 1, 0, 0, 1. Okay, so let's have another example. So let's try 0. So 0 can be written in binary as 0, 0, 0, 0. And then let's copy this and apply 1's complement. Every time we invert bits, we are applying 1's complement. So this is now the inverted version of 0, 0. So what we get is 1, 1, 1, 1. After inverting, we add 1. So this becomes 1 plus 1. This becomes 0. Carry 1. 1 plus 1. This becomes 0 again. Carry 1. And then 1 plus 1. 0 again. Carry 1. 1 plus 1. 0 again. And then carry 1. And then since we are working on 4 bits only, so we have an excess. So this becomes an overflow. So we drop off the overflow. So what is left here is 0. So this means that 0 has a value of 0, 0. So we were able to retain 0 to become 0. So we don't have a second version of 0. Unlike with our 1's complement, we have positive 0 and negative 0, which is not really applicable in real life. So for 2's complement, we maintain one value for 0. So 0 is always 0. So let's have more examples. So this time, let's apply complement shortcut. So let's say we have 6. The binary form of 6 is 0110. Now, what we are going to do is to copy this, and then what we will do is to copy all the bits from the right going to left. Starting from the right, going to left. Okay, we'll copy that, and then on the first occurrence of 1, we stop copying. So this is the first occurrence of 1. So let's copy 0, so that is 0, and then let's copy 1. So there you go. And since we have already encountered the first one, then for the remaining bits, we have to invert this. So this one becomes 0. And then for this bit, this becomes 1. All right. So this means that 1010 is equals to negative 6. Okay, so that's how we do the shortcut for 2's complement. So we did not add 1 to it, but we take a shortcut so that we'll be able to make it easier. And then let's have another example. So let's try 56. Let's try a bigger number. Since this is a two-digit number, we will use 8-bit binary. So the binary form of 56 is 00111000. So the next step that we will do is to copy this. After copying, we'll copy those bits starting from the right, going to the left. Okay, so let's start with this. So let's copy the 0. There you go. And then another 0. There you go. Another 0. There you go. And then the first occurrence of 1. After copying the first occurrence of 1, the remaining bits will be inverted. So this one will become 0, and this another one will become 0, and then the two remaining 0 will become 1. There you go. So this means that 1100, 1000 is negative 56. Okay, last example, let's take 23. 23 can be written in binary as 0001, 0111. Let's copy this, and then let's try copying the first occurrence of 1. Since we have already encountered the first occurrence of 1, we have to invert the remaining bits, starting from this point, going to the left side. So this becomes 0. So we invert. This is also 0. This is 1, 0, and then the remaining zeros will become 1. There you go. So this means that 11101001 is negative 23. So that's all for this video, and see you in the next lectures.